Good evening once again, and once again welcome to this course on convex optimization. In the last lecture I had spoken about how can we surmount the difficulty of non-differentiability, which you can take as a bane or a boon in convex optimization. Possibly convex optimization is richer because of the presence of non-differentiability of convex functions and the fact that optima lies precisely at those points. Now, what I want to reiterate is that we had introduced the notion of a subdifferential of a convex function. So, given a function from Rn to R, the subdifferential is the collection of all V in Rn such that this condition holds for every y. Now, what we had known about this case is that del f x is non-empty convex and compact, and further we had written down an optimality condition in the unconstrained case, the necessary and sufficient optimality condition, the Fermat's rule in the convex case, which is the famous condition 0 belonging to del of f x. This is the necessary and sufficient condition for a point x to be a global minimum of the convex function over R, the whole space R n. Now, if I claim that del f x is replacing the derivative at non-differentiable points, then I need to show that it exhibits a calculus, just like ordinary derivative exhibits a calculus, that if you take the sum of two derivatives, you take the sum of two functions and take the derivative, it is nothing but the derivative of the sum of the individual functions. So, there is also composition of two functions there, and then taking the derivative of that. Whether such rules do work in this case, it is very important to know. Of course, we can give a lot of examples which will come very soon, but it is very important to know at this outset that this mapping, the subdifferential, takes an element x in Rn and puts it into a convex compact set. So, del f symbolically is written as a mapping from Rn to Rn, but it is a special type of mapping. It is called a point to set mapping. Or set valued mapping, whatever you want to use. Now, remember, so when we are trying to build a calculus for this class, this sort of things, we have to really appreciate the fact that every time we are dealing with sets, we are no longer dealing with numbers or we are no longer dealing with vectors. So, these are sets, and so it is very, very important that we take utmost care when we are talking about sets. So, if I want a calculus rule, so what sort of calculus rule I can think about? Okay, let me think about one rule, which is the sum rule. So, you take two convex functions f1 and f2, and take their subdifferential at a point x. Do you have this rule? Do you have something like this? That is the question. The answer amazingly is yes. this holds. But let me tell you that here this is a set and this is a set. So, if I go back and try to understand this writing, then here we are talking about the equality of two sets. So, here for example, what is the meaning of this set? This set means is a collection of all z which is written as V1 plus V2 such that V1 belongs to and V2 belongs to del f2x. Now, if I want to show the relation back and forth, so what I really have to show is that first I have to show that and then of course I have to show that so A subset of B and B subset of A, so A is equal to B. Now, all these are quite easy to, this is quite easy to prove, you have to just write down the definition. This would need a little bit of hard work. See, if I take a V from what would happen? So, can I do something with it? Our idea would be to use the directional derivative and the fact that the directional derivative acts as a support function, that is the better idea would be to use this fact that if I take the directional derivative of x, directional derivative of f1 plus f2 in any direction h, then this is nothing but this is a simple calculation which you can easily do. So, once I have this, what does this mean? What would this mean? It would mean that this is nothing but max of all V element of del f1 plus f2 x V of h is equal to max of, max because it is a compact set. So, V1 of del f1 x V1 h plus max of, I am just writing down this definition which you, this relation which you already know, we have studied in the last class. So, from this can we conclude that this is equal to this? We can actually conclude that, because this fact, in fact one can write this whole thing in a much more compact way. Or V1 plus V2h, does not matter. So, if the support functions of two sets are equal, so this is called a support function. So, this is called a support function. If you have I have a convex, take a convex compact set, in fact it works for any convex set. but let us just talk about convex compact set. Take a convex compact set and take this V. So, I am calculating at any, okay, maybe I will remove V and make it look like x. So, I am computing this at any x in Rn. So, how do I compute? I need not write sup or max is the same thing. It will consist of all V element of C such that I want to find the minimum of this problem, the maximum of this function x of V, x is fixed over all V element of C. So, what you can prove is that if you have two convex compact sets and you have this, so what you can prove that if you have convex compact sets, then this is equal to this if and only if C is equal to D. This fact would lead us to conclude this fact, this one. Okay. So, one of the major calculus rules looks like it works for subdifferentials. Now, okay, I would like to know that, okay, if you have multiply a function by a constant and then you take its derivative, then the constant comes out and the new derivative of the new function is the constant times the derivative of the old function. So, if I take lambda of f, where lambda is greater than or equal to 0, you see if I take a negative lambda, then lambda of f need not be convex anymore. So, now I ask myself the question, how do I compute this subdifferential if I know the subdifferential of f? Then, by the way, you can understand it is not so easy to always compute subdifferentials. Now, for example, if you take the function norm of x, then the norm, the Euclidean norm is only non-differentiable at the point 0, and I leave it to you as homework to prove that this is nothing but the ball of radius 1 centered at 0, or more handy is this notation B, is called the unit ball in Rn. You can also find a composition rule and all sort of stuff, but there is something which actually differentiates convex calculus from the standard ordinary differential calculus, and that is the notion of a max function. That is, here we are going to talk about a convex function given as a maximum of, say, m other finite valued convex functions. Now, suppose all these are even differentiable, all these convex functions are differentiable. My query would be to find, now here is a point where we are absolutely coming into a different paradigm, because whenever you have a function created out of maximization or minimization of some other class of other finite number of functions, then the resulting function is not differentiable in general. So, there is nothing, you cannot define the derivative of grad f, there is no way you can do so. So, if you have these are differentiable convex functions, then this is a convex function, but need not be differentiable. And also I want to emphasize why this function is important, because most of the non-smoothness or non-differentiability in convex optimization and in optimization particular arises not in some arbitrary manner, but in some very ordered fashion by taking maximization or minimization of few functions. For example, if you look at the standard well known example which we had been giving in the last lecture, the absolute value of x when x is r. So, this can be written as max of x and minus x, these two functions. So, this is my f1 x and this is my f2 x. You see, even the most standard well known thing can be expressed as a max function. So, how do I find its sub differential? So, in fact, I am just now going to write both the directional derivative as well as the sub differential. So, let me first write down for that class of functions the directional derivative. This is max of the gradient of f I x in the direction h, that is the inner product of grad f I into h, where I belongs to j of x j of x. So, what is this j of x? J of x is some sort of indexing of where the maximum is attained. The j of x is the set of all indexes I from 1 to m. So, among those indexes, find the ones such that f I x is equal to f x, because if you put an x, there would be one function at least for which where the maximum value would be attained, because we just have finite number of functions. There could be more than one. So, for a given x, there could be 2 indexes here or 4 indexes. For another m, there would be say only one index. So, it all depends in fact on the choice of your x. So, we have to make this set depend on x. This is called the indexing set or index set. Now, if you look into this very carefully, you will observe something, that what I have done, I have taken maximum of these things over this. So, I am taking maximum of some real numbers and that is giving me this stuff, right. Now, this if I now compute the support function or compute the support compute the set whose support function is this, then the sub differential of f at x is the convex hull of all elements of the form grad f j x, where grad f I x, where I again belongs to j of x. So, you take few elements and take a convex hull. So, this set del f x of a maximum function is a polyhedral set. Polyhedral set, which is quite interesting in its own account. So, we will see that how this idea can be used to derive the optimality conditions for a differentiable convex programming problem. We will show that a lot of any optimization problem, you take a convex optimization problem, minimize f x subject to g I x less than equal to 0. Now, I can always express this problem as a convex optimization problem with only one convex constant. Let me assume that f is differentiable and all the g i's are differentiable. So, this is convex and differentiable. I will not always write convex, because we are only talking about convexity, we are not talking about any other class of functions. And then you can write this problem is equivalent to minimize f of x subject to g of x less than equal to 0, where g is a single constant, where g x is max of max of g 1 x dot 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 g m x. So, you see any convex function with many constants can be written as a convex function with a single constant, but there is one lopsidedness of this whole issue, that you lose differentiability of the constant function. But that does not mean that we have lost everything, because our mathematical structure is very well done, because we already have a clearly done explicit formula of how to compute the subdifferential of this class of functions. So, this sort of function. So, let me go ahead again. We had all now only been talking about convex functions from Rn to R. But in the beginning we said that in convex analysis and convex optimization, it is natural to have convex functions from Rn to R bar, where R bar is R union the two infinities, and we wrote down some rules for how to handle the infinities. Now, can I define, if I have a convex function of this form, can I define a subdifferential of this function? The answer turns out to be increasingly interesting, and it is yes. So, take f from Rn to R bar and assume f to be proper. So, there is at least one point where the function is finite. So, let x be a point where f is finite. Then del of f x is defined just in the same way. Note that if there is a y for which f y is plus infinity, that does not break this equation at all. So, this y has to be over all the Rn, all y in Rn. So, if but x cannot take, f x cannot take the value plus infinity, then it would become meaningless. So, f y can be plus infinity, that does not harm the equation at all, and we will just give an example of that. Now, what happens if x is a point where f is not finite? Then del of f x is defined to be the empty set. But there is a word of caution. It does not at all mean that if del of f x, that if f is, that del of f x is non-empty for every point x where f x is finite. No, there are problems where at the point where f is finite, this set becomes empty. So, the story that we had for Rn to R is, now you see it is getting complicated. Now, let us do a little bit of example hunting for this class of functions. Now, a very important class of functions in convex optimization is the use of the indicator function of a convex set, which takes on the value 0 if x belongs to C and takes on the value plus infinity if x does not belong to C. We have already mentioned this earlier. Now, this is a convex function from Rn to R, and it is a proper convex function because it does not take the value minus infinity, and over whole of C it takes the value 0, which is a finite number. The question is, what is this? Is something very interesting. So, del of del C x here is a set of all v such that v into y minus x is less than equal to 0 for all all y element of Rn, sorry, all y element of C. Now, how do you prove this? This proof is quite simple, because if I write down del C y minus del C x, you see x has to be in C, because otherwise it is not finite. So, if x is in C, this is always 0, and here it is either 0 or infinity. So, suppose y is such, y is not in C, then del C y minus del C x is nothing but plus infinity, which is greater than v times y minus x for all v in Rn. So, whatever v you take, this is anyway true, because this is a number and this is obviously less than plus infinity. Now, if y is not, sorry, if y is now in C, then del C y minus del C x is equal to 0, and any v which has to be a subgradient has to satisfy this. Sorry, for has to satisfy this, sorry, this is, so here because we have taken a particular y. Now, so we have covered the whole, all the y in Rn. So, the common v which satisfies both is the v which satisfies this, and exactly that is what we have written down there. Now, this class, this particular type of set has a particular name, and if you observe that very carefully, this is a convex cone, and this has a particular name called the normal cone to the convex set C at x. We will come to the normal cone business very soon, but before that let us, we will do something else. We will try to write down some optimality conditions. Now, we will not bother much about this at this moment, the geometry etc., will come later on, and which is a flourishing geometry which has lot of interesting things. The subdifferential. So, what we have, the subdifferential of the indicator function is the normal cone to C at x. This is a fundamental result in convex analysis, and this result has led to the development of subdifferential calculus for non-convex function. This is truly a fundamental result, and this is called the normal cone, which we will talk later, details later. Now, okay, you will again come and ask me a very important question. Okay, now you have defined subdifferential for a class of functions which is extended valued. Now, can you give an example where the function is finite at those points, but does not have a derivative at the, does not have a subdifferential at that point, in the sense that the subdifferential is empty at that point. So, that is the example that we will show. Now, let us look at this function f x is minus root over 1 minus x square when x is lying between minus 1 and plus 1. So, x is obviously in R in this case, and it is plus infinity if it is outside. Now, this function is a convex function. This you can try to sketch the graph in MATLAB homework. You sketch the graph in MATLAB and then check the epigraph and see the epigraph. Also, you observe that if I take put x equal to 1 or x equal to minus 1, at that point the functional value is 0. So, it is finite, but it does not have at that point non-empty subdifferential. The subdifferential at that point is empty. So, your homework is to find, try to calculate del f1. The answer to this question is del f1 is equal to phi. Now, there are a lot of issues which come up when you take this extended valued function, though they are very important. The issues are this. Now, we have said that the subdifferential for a function from Rn to R is convex, compact and blah blah, nice look, nice thing. But what happens when I have this sort of an extended valued function? Let me just take a very simple case. So, f x is equal to 0 if x is 0 is equal to plus infinity otherwise. If you look at the graph of this function, so this is the graph of this function x equal to 0, 0, 0. So, the epic graph is nothing but the whole y axis. So, epi of such this function is the y axis. Now, here the function value is plus infinity, here the function value is plus infinity. Now, if you look at the subdifferential at 0, because that is the only point where the function is finite, del of f 0, of course, the function is not differentiable, there is no question of differentiability for this extended valued stuff. So, del f 0 here is R, and R is of course not compact, though it is convex and closed. So, a subdifferential is always a convex set and a closed set, but it need not be bounded always. So, this is a very important example which shows that. When does a subdifferential become closed, convex and bounded even when the function is extended valued? The answer is as follows. So, if x is in the interior of domain of f, and you know what is the domain of f already, the domain of f is a set of all x where the function is finite. If you take the interior of the domain of f, then it would imply that x, that the subdifferential of f at that point is always non-empty and convex and compact. That is, of course, the dome f has to have an interior. We are expecting the dome f to be full dimensional. If it is not full dimensional, nothing can be said. So, if here the dome f here was full dimensional, but the interior did not exist, right. So, whatever neighborhood you take, it is outside the set. So, del f x is non-empty, convex and compact. Okay. You will now ask me a question, okay, take the function from Rn to R, go to a simple case. Of course, many optimization problems would be of this class. Now, if f is differentiable at x, do you have this fact that the subdifferential contains only the gradient? The answer turns out to be yes. The subdifferential has only the gradient, and that is why the subdifferential idea is a true generalization. You know, if one might ask, why can't you have some other idea to define something which can imitate the derivative, but other ideas like using the notion of weak derivative from distributions did not work well, and it is the intrinsic property of the epic graph, which is a convex set, came into being, that that at the point of non-differentiability of a convex function, the epic graph has a infinite number of supporting hyperplanes, and that is a fundamental idea that builds into the making of the subdifferential. That is, if you have a convex function which is not differentiable, say you have a king point here, then if you look at the epic graph which is a convex set, then at this point there is not only one tangent hyperplane, there is many supporting hyperplane. So, this is the fundamental idea that is built in, that this is just a convex way of bringing in the fact that slope of the tangent is a derivative. That is brought in through the convex language, which is the language of the supporting hyperplanes, and which brings us to a set rather than just a vector, which is a curious and important point. Now, Suppose I have a point where the function is differentiable, so suppose it is x, then let us see f of x plus lambda v minus f of x is xi times lambda v for all xi element of del f x. I am just writing the subgradient inequality. If I do so, now bring out the lambda. So, f of x plus lambda v minus f x by lambda. Now, the function is differentiable, you can use the Taylor's theorem or the differentiability definition to come up with the situation that if I now take the limit as lambda tends to 0 from the positive side, then what you will finally get is this, and this by differentiability you know this is nothing but grad f x into v, grad f x inner product v is grad of v. So, the directional derivative is nothing but the gradient into the direction of taking the derivative. So, directional derivative is gradient in the direction v. So, this would simply mean grad f x minus xi v is greater than equal to 0, but this v was arbitrary. So, it is for all v element of R n. So, now what we are getting that I am having a linear function which is non-negative everywhere, it cannot happen. So, which it cannot happen unless grad f x minus xi is equal to 0. See, you have a v. So, you could take xi minus grad f x as one of those v's and put it here to get the norm of grad f x minus I whole square less than 0. So, grad f x would be xi. So, for whatever xi you take, grad f x would be xi, and that is exactly what you want to show here. The question which is of immediate importance to us is the following. Now, if you have two functions proper f 1 and f 2, proper and convex, proper, convex, and we will add a little bit of thing. It is lower semi continuous, LSC. I hope all of you, lower semi continuous means that the epigraph of these two functions are closed. The epigraph is a closed set, that is the meaning of lower semi continuity. It is an if and only if condition. It is something beyond continuity. We have already known that if a function is from R n to R, if it is a convex function, it is always continuous, but if it is from R n to R bar, we lose continuity because of this adding these infinities, but we have something more which is lower semi continuity, because continuity cannot be, this lower semi continuity can be characterized by epigraph. So, even if continuity is lost at the boundary of the domain, but still we can have lower semi continuity. So, if I have this and if I have the following result, which is extremely important, that I will consider that my domain of f 1 and domain of f 2 are full dimensional sets, in the sense that they have interiors, they are nice sets. Suppose interior of the domain of f 1 intersection interior of the domain of f 2 is not equal to phi, then you have this fabulous fascinating result, some rule, that too for a class of functions which is extended valued. This is a very big advancement in convex analysis. This is called the Moreau-Rockefeller theorem. Both of them one of the greatest convex analysts and optimizers of our time. He is a French, he is an American. Rockefeller is famous for his book Convex Analysis. he is mostly worked in mechanics. Moreau, Jean-Jacques Moreau from France, and Rockefeller from Montpellier actually in France, and Rockefeller was in Washington, Seattle, and still is. Okay, this is one thing. Another is that you can do it like this. Now, suppose there exists an x in, so this is one condition under which this is true. I am giving you another condition. Suppose there exists x in dome of F1 intersection dome of F2, where F1 or F2 does not matter, where F1 is continuous, then del of F1 plus F2x is equal to del of F1x plus del of F2x. So, this is again a fabulous result. So, now what is the use of such a result? Why we are so interested in these extended valued convex functions and what we want to do with it? We want to find out the optimality condition that we had been looking for so long. What have we been doing? We have been looking into this aspect. We have been looking into this following fact, that I have a convex function f x to be minimized and x is belonging to C. I want to find a necessary and sufficient optimality condition when f is no longer differentiable. Now, if that is so, how do I find an result? We had already done something exactly, that we have shown that if x bar is a global minimum of Cp, then for each x this is true. Of course, if this holds, then x bar is also a global minimum of Cp. So, then what we can do is that this Cp, then this holds, and this result, the converse is also true. The converse is also true. Now, what I want to say is that here there was a problem. My xi x was changing with every x, but xi x was belonging to this, but it was changing with every x, because of course, you are using this compactness issue and all these things. Now, what I want to assert is that I do not want the xi to change for every x. So, that is exactly where we need to look into our story. Now, what I will do is the following. If I call this problem as Cp, then x bar is a minimizer of Cp if and only if x bar is also a minimizer of the problem mean of f plus this is the problem over x element of the whole Rn. So, now we are talking about the extended valued function. You can prove this very easily. This is homework, this is too easy to prove. You might ask, okay, what is the big deal then? Of course, x has to be in C naturally, and so what is the very big deal? Okay, this happens. So, how do you get an optimality condition? This is as follows. If f is proper if f is a proper convex function, then x bar is a global mean. Of course, x bar has to be a global mean, means it f of x bar is finite, otherwise it has no meaning. X bar is a global mean or global minimizer if and only if 0 belongs to del f x bar. So, this Fermat's rule remains relevant even when we are talking about proper extended valued convex function. Of course, here we are taking f from R n to R bar. So, this remains relevant even if this holds, even if this function is extended values, this fundamental result remains relevant and remains true. So, once I know this fact that okay, if I have an x bar which is solving this, x bar is solving this unconstrained problem. So, this is result is for unconstrained problem. So, x bar is a global minimum of maybe of f on R n if and only if this holds. So, x bar in here is a global minimum of f plus the indicator function over whole of R n. So, what I will get? I will get 0 belonging to del of f plus. Now, what is the domain of the function f? It is whole of R n. So, and what is the domain of the function del c? It is whole of c. So, domain of f1 intersection domain, sorry, domain of f intersection domain of the function del c is nothing but c, but the function f which is f1 is taking, f is taking the place of f1 here. This function f1, sorry f1, this function f1 is continuous. So, this function f1 is continuous over whole of R n. So, it is naturally continuous over c. So, this condition is satisfied for this particular case. So, now I can write the sum rule. This would imply that 0, because this is equal to del of f at x plus del c at x. So, sorry, at x bar, because I have said x bar is the minimum, right. Okay, right, x bar is the minimum. So, we will now have, so what I will have, well, what I will have, because and f is of course continuous over c, continuous on c. So, this will lead us to the fact that del of f plus del c of x is del of f at x plus del of del c at x. So, what we will conclude from this fact is that 0 actually belongs to del of x plus del of del c of x, and 0 belongs to del of x plus, this is what we have symbolically written as normal cone to c at, sorry, at x bar, x bar, x bar, x bar. So, this is one of the famous necessary and sufficient optimality condition for a convex programming problem, and it is called the Rockefeller-Shenichny condition. Shenichny, it's Russian Shenichny condition. Now, observe what I have from here. This says that this implies that there must exist a v in del f x such that minus of v must belong to this for some v element of, no, for some, sorry, or there exists, or I should write nicely, there exists v in del f x bar such that this happens. So, this translates to this, which is very simple, because there must be a V in del fx bar and W here such that V plus W is 0. So, minus V is equal to W, which also belongs to normal cone. So, this is what we have. So, what does this mean? It means there exists V in del fx bar such that minus V into x minus x bar, because that is the definition of the normal cone, which is same as of course the del of this, and you have already seen what is the formula. So, for all x in C. So, now we have improved upon our initial understanding, initial optimality condition. We have improved and showed that I can have a fixed V which will work for all the x's. So, I will have a fixed V such that V into x minus x bar is greater than or equal to 0 for all x. So, the Rockefeller-Shinichny condition can be written down. So, we have strengthened the optimality condition which we have done in the last lecture. So, with this we stop our lecture today, and then in tomorrow's class we go into some more relevant issues in convex optimization and convex analysis called the conjugate of a convex function, and that has deep links with optimality and the optima itself, and we should explore this, because this conjugate convex function would help us in many ways as we will go along. So, for today let me tell you a good night and thank you very much.